Good afternoon. So this is sort of a follow-up video to my all the forces, and only let's focus on sort of the EM-ishness of it. Okay, because I was thinking about it the other day, and the way I think about it, the way that I think math and quantum mechanics thinks about it is there's sort of like these three fields, right? There's the electrostatic field, there's the electrical field, there's a magnetic field. There's gravitational, but that seems to be, I think that's a summation of all of them, essentially. It's the total energy, and only it's a very, like the curve doesn't even manifest until very high energies. There's no way of noticing it until you get to these extremes where you have to be at over, I mean, if 10 to the 64, is that the number around there? If 10 to the 64 is a limit, then why would we expect to see much a lot of the time until we're at least halfway? Halfway on a, I mean, there's halfway, and you barely knocked into what will be an insane effect. Such as logarithmic proportionalities and stuff like that. But today's video is supposed to be focused on, I even have a list so I can stay on track smartly. Okay, so let's imagine we got some space, and we have, space has a totally random collection of vectors to it. It's entropic, basically. It's like a bunch of entropy. It's just like random noise, right? This is the vacuum energy. It's random and therefore sums to almost nothing, but not nothing, which is where the neutrons come in. Because if you look at the cosmological at lambda, it's like lambda is set to be almost exactly the minimal density of what we find in space, of course, because that's what we see, which is like 1 neutron per cubic meter. Anyway, so you have this random collection. There is the energy, there's as much energy, there's this ton of energy here, but it's not very organized. It's very poorly organized. Right, it's random, it's noise. Sum 0. Okay, so let's get that a little organized. Let's not go straight to laminar. Let's start with electrostatics. And instead, I'm going to designate locality. And then I'm going to have all these charges organize themselves relative to locality. Right, there we go. An electrostatic field. And whatever, if this was positive or negative, if this was negative, actually let's make it positive, like it was a proton. Ooh. Right. So therefore, what we would have, this would be a proton, so all the negative charge would be attracted to it. Right? So what you'd want to have would be some region out here, ideally, and then it would drop off. But if positive was actually an inflow, as I suggest, then this would be a source of inflow for this outflow. This is a drain. This is space. This is drain mass. Space. This is distant void. This is a black hole. There we go, though. Right? Electrostatic charge being spherical. right? And therefore, having a squared drop-off. Okay. So that is charge, right? It's sort of like this radial designation. Then we decided, no, actually we're going to make this charge move. Like this. Okay, so this is just a charge sitting, doing nothing. Now we have this charge moving. And let's see, we get a bunch of charges moving. Right, but they're laminar, they're all like, right, they're all going this way. Laminar, right? But what does that do according to Bernoulli's principle? Well, if you had a laminar flow in this direction of C, what you would end up doing, of course, is having a very low pressure zone here in this conduit, your wire, where your electricity is flowing, or the energy pressure is flowing, which creates a negative pressure, which draws energy in this way. Okay, this is electrical. This is the electrical field, but what we know about the electrical field is that there's this, it's not this, like this weird chirality thing about it, right? And why? This makes sense, the Bernoulli thing. But why doesn't this stuff just flow in and there's like, you know, even if that happened, of course, even if flew in, this is forward, this would be an outflow in here. Right, this is outflow from the wire and this is inflow from the wire. But that's just electricity. Let's do a cross section now for a second. Okay, so we have a conduit that has a flow in it. And I'm going to get chirality and therefore magnetism out of this. Because right now there's no chirality really, right? The flow should just be into this wire. Okay, but here's the wire, and we're going to use that like that's an arrow going away, so this is flowing that way, away, right? And we have this traction in, right? This is the we're now seeing the field, right? It was planar. Now this is flying away from us, which creates a low pressure here, which sucks things inwards towards it. But where's the chirality in it? It's just like this. That you can't flow into this, right? This is too busy. This is like, so instead what happens is that everything goes like this. Right? Developing that chirality. So now we have this chirality, which is magnetism, but it's not really manifest because it's in this weird flow pattern, which I think I mentioned in that previous video. I had a notion about how to wind a magnet that I've never seen before. It could create a strange, it might be useful for those nuclear reactors. Okay, wait, we had our wire, right? That had that field. We know it has a little bit of a twist to it, right? So now what we're going to do is let's take that wire itself. See its loopiness. Take that wire itself and make it into loops. Right? Ooh, magnetism for kids. Okay, so let's say we're going inward there, outward there. Let's say that the twist was arrow pointed. What did I have it going? Counterclockwise, I believe. So it's like this sort of to the inside. This to the inside. It's all going on the inside, but this is the chirality component only, really, right? Like the flow of the electricity is doing this loop-de-loop, but the chirality itself. So it's like each of these is a stage forward. But when I want to point out, so there we go, now we have magnetic field, magnetic flux. There we go, magnetic flux as the chiral component of the electron flow. And again, this is going to see. But magnetic fields, as I can't remember, but I know the flux propagates at c, doesn't it? Yeah, it all moves at c. Everything's just at c. Because all the Plancks are connected, so I guess that's the speed everything goes. 1 Planck per unit Planck rotation. You know? 1 Planck per Planck. Okay, that's why when Plancks are smaller, you don't seem to go as far. There we go, magnetic field. Oh, but what I wanted to point out in this is interesting that while we think of the three electrical fields as being 90 degrees to each other, so let's say this is the static, let's say this is electric, because you add a dimension sort of. Static is still, you make it flow, you give it a dimension, it becomes the electrical field. Then the magnetic field is where you take a straight line, which is one-dimensional, and you make it a circle, which gives it a planar aspect, a two-dimensional. So you've got like this, right? But there is no jumping back directly that I know of, that I've ever seen, between magnetism and static, because they are additions of dimensions. So it's like it's going deeper, it's adding a twist, adding a twist. You have to come backwards out of that hole to get to the surface, sort of thing, because each one is an added convolution, texture of convolution, right? There is no jumping straight back. These are not actually linked. These are like, it's like one is a curve in one direction, one is a curl, like a curl in one direction, or it's like a flow, then a curl, then another curl on top of that curl, creating a sphere. But there's no getting just directly back from the sphere to a simple outflow, because you're contained already within the sphere. What this relates to, what was this? Oh yeah. And then the whole point of this sort of, except for just like nicely going over, I just like to go over in my head the way all the forces interact with each other, you know, so that you really get a feel for them. Okay, so what this relates to is neutrinos, because I see neutrinos as, okay, make an atom. Let's make a neutron, right? Because with neutron decay, you get an antineutrino. So, here we go. We'll go through my favorite process of creating a neutron. So, we are now using red instead of the yellow. In my book, I use yellow. This is a negative. Right? Negative. Negative. That's a 2 down. Here's an up. It negates them. 2 positive, positive. You know, my proposal, very straightforward proposal in all of my thing is that what happens here, well, this is a neutron, right? So what happens is this turns into a photon, and that turns into a photon. Okay, a positive and a negative, they become a photon. Photons trapped over their own gravity, and thus now with inertia held in space, and there's a couple of ways you can look at that. I think I have sort of like there's the 2 pi Planck photon approach, which I guess is the quantum mechanical approach. And then even from a sort of classical approach, the E equals mc squared approach, I go, well, then m is equal to E over c squared, right? You get some energy, and you spread it over a sphere of infinitesimal size, Planck, and you have it spin, you have it rotate at c, but it's rotating in all directions simultaneously at c, which means that every point on the surface gets induced angular momentum of c squared, because when you rotate something, there's the radius, and then you get this, and it's squared. The velocity squared is the induced momentum there. So yeah, so that's sort of what I consider to be the classical way of deriving from E equals mc squared, because you're just using a rotation of as if it was a piece of mass, but it's infinitesimal energy over an infinitesimal, so we get the mass out of it. So anyways, boop, neutron, right? Then neutron decay this, what was a photon, with two charge components, a positive and a negative, becomes a proton, which is a mass, but also an inflow, a positive charge. And am I blocking it all with my arm the whole time? Probably. And electron field, ginormous. This is the solution for all the fine tuning and everything like that, but relevant to this, boop. Okay, so when this happens, how this relates to neutrinos is there's the three axes, right? I said it's like bound. And what happens is one by one, it was completely bound. It then loses its binding in the magnetic realm, right? And then it loses its binding in the, like, as a flow. And then the very last moment, it's back in the static realm, which is why it's charged, and which is why I think that the electron neutrino, I don't know if that's symbol for it. No, that's the electron and neutrino. But the electron neutrino is the sort of like the lowest, seems to be the lowest energy version, is because that's the most evident. You'd have to have one that's like really, really, really wobbling like crazy to see these parts of it, right? To get this part right away. Whereas the electron is sort of like the most evident. It's the first layer that you come to. It's the most evident layer. So you end up getting the electron neutrino as the lowest energy one, because each one is a convolution. Each one is a development, you know, in a dimension, and therefore it takes a curl, and therefore that's a bunch of energy turned into rotation. Okay, that's it. Peace.